Hey everyone, it's Mr. Montgomery again. Today we are diving more into magnetism and we are talking about the Earth as a magnet. Is it a magnet? Does it have the same properties as a regular magnet that we use all the time on our fridge and all that kind of stuff? Well, we're going to find out. So, after this lesson, you'll be able to explain the Earth's magnetic field. But before we even jump into all that really cool stuff, we have to do a little bit of quick history, which is not my strong suit, so bear with me. In the late 1600s, there's this goofy looking guy over here, right? Wearing all these weird clothes that, well, it looks weird to us anyway. His name was Sir William Gilbert. He experimented a lot with compasses. And after messing around with these compasses for so long and seeing how they work and act, he hypothesized. Now remember, a hypothesis is an educated guess. So he hypothesized that Earth has a magnetic field surrounding it. But for this idea, just like many people back then, he was ridiculed by other people. And if you're not too sure what ridicule means, maybe you never heard that word used very often, it just means he was made fun of. People thought he was crazy, stupid, a whole bunch of mean stuff, right? But the joke is on them because he ended up being correct. There is a magnetic field surrounding the entire Earth, and just like any bar magnet or any magnet we come in contact with, for a matter of fact, there are two magnetic poles. And just like we already learned, there would be a north and a south pole. So, the Earth's magnetic poles are located near the Earth's surface where the force is the strongest, right? Makes sense so far. But the magnetic poles are not in the same place as Earth's geographic poles. See if you'll let me zoom in a little bit. There we go. So if you zoom in on this picture, whoop, you'll see that there are two different kinds of lines. We have this green dotted line, and we have this solid black line. The solid black line is that imaginary line that we put directly through the middle of the Earth, right? We call it the axis. So that is what we could also call true north, or the geographic north, the very, very top of the world, right? And this green dotted line is the magnetic north. So if you have a compass, it's going to want to point to magnetic north, not true north. So that means if you're hiking around the world and you don't have a calibrated compass, well, you're going to be walking more towards northern Canada than the North Pole itself. So be very, very careful. So let's do a quick check in. We have a very quick true or false question. Magnetic north and geographic north are the same locations. What do you think? Were you paying attention? We'll find out. Which one do you think it is? Is it true or false that they are the exact same location for magnetic north and geographic north? Do you have an answer? Okay, so it's false. They're not in the same spots. Magnetic north is more in northern Canada, and geographic north is, well, that's the North Pole. All right, and now we're going to get to see a lot more clear the difference in locations. So Earth's magnetic pole in the northern hemisphere is actually located in northern Canada. That's this red dot right there. And then geographic north, or what some people call true north, is this green dot at the very top of the world. See, I know it might not look like a huge distance in this little picture, but trust me, this is thousands of miles apart. They are very, very far apart. The Earth's magnetic pole in the southern hemisphere is actually located in Antarctica. And this is going to be one of the few times you'll ever hear me say something like this, where the true south or south pole is actually in the same country as magnetic south. Because Antarctica is so huge. I mean, how could they not be? It's ginormous. All right, let's see if you're paying attention to where exactly magnetic north and magnetic south would be. So, I know you guys can't really draw in here, but I want you to place your fingers in two different spots. Show me, or show yourself really, because I can't see what you're doing. Let's be honest. I got no idea what you're doing. For all I know, you're eating a bowl of cereal or you're getting pizza all over your Chromebook. I don't know. But point to a spot at the top of this little map. And yes, this is a map of the world. It's just kind of unwrapped, right? Kind of spread out. There's a spot north for magnetic north. I also want you to do your best to point to the correct location for magnetic south. I'll give you guys a quick second to do that. Alright, do you have your spots? Alright, so first I'll use blue for north, right? And magnetic north is right around somewhere right there in northern Canada. Alright? And then magnetic south, well, it's not going to be perfect, but it's going to be kind of like right here, somewhere in Antarctica. I'm not as worried about you knowing exactly where magnetic south is because Antarctica is a huge, ginormous block of ice. We're not really exploring there, okay? But in northern Canada, we can pretty easily get to northern Canada. Okay, so is your compass pointing in the right direction? Since compasses point to magnetic north, because the magnetic fields are kind of taken over. Instead of true north, this must be taken into account while using your compass. This deviation between magnetic north and true north is called magnetic declination. So I know this word deviation is probably maybe a little weird for you. Maybe you've never heard it before. It's a math term, actually. When you'll start learning about standard deviation when you finally start learning statistics. The deviation just means the difference between these two parts. That's it. So if you understand that magnetic declination is the distance or difference between true north and magnetic north, you're all good. Don't worry about it. Alright, since Earth has such strong magnetic fields, Earth itself can make its own magnets. And you know what? The more I read that, the more I feel like it just sounds like common sense, right? Because we can find magnets in the Earth. We have all this ferromagnetic material that we kind of learned about, iron and whatnot. So, of course it can make its own magnets. It's just that we don't usually think about it like that. So the Earth's magnetic field is so strong that it acts on the rocks that contain magnetic material. And I would say most of our magnetic material is going to be iron. It's super abundant. We have it all over the place. It has magnetic domains all over in it, and we can easily manipulate it and make really cool electromagnets out of it. Alright, so for example, right here, the example, I'm not just talking gibberish. Iron in the Earth's molten rock lines up with the Earth's magnetic field. So, as you guys probably learned a couple years ago, right, we have the Earth's crust, we have the mantle right down here, and we have all this molten rock, or as we could call magma. Right in this magma, there's just tons of different kinds of materials. We have silicon oxide, we have iron, we have whatever other kind of rock you can literally think of. Probably lodestone mixed in there. You have, oh gosh, really anything you can think of. But it's all swirling together. And wherever it's concentrated the most, that's what's going to manipulate the magnetic field, especially iron. It's just constantly swirling underneath the Earth's crust non-stop. All right, and this I just thought was just so cool. So the Earth's magnetic field actually, or I should say, its north magnetic pole changes location over time. How crazy is that? And you can see in this picture right here, it's actually started up here, it kind of zigzagged around, and as time goes on, now not just days or months, but years, as years have passed, its magnetic north has changed its location. It's actually getting quite close to the real North Pole. And in the trajectory it's currently on, it looks like it's actually going to pass through the North Pole and maybe actually end up more towards Russia. So in a few years, we might actually start saying that the magnetic north is not in northern Canada. We might be saying something like, hey, it's actually in northern Russia, which feels kind of weird, but it might happen. We gotta wait and see where this trajectory takes us, or maybe it might stop closer to the North Pole than we think. That'd be kind of cool if it lined up and made things a lot easier for us, right? So the magnetic field's impact on iron in the Earth's rocks alters the magnetic field over time. It is not fully known why this happens, though. Well, when you have all this molten rock and iron is part of that molten rock, it kind of makes sense. I mean, that's just me. But if you have all this molten iron that has all the same properties as regular iron because it's the same elements and it has the same atoms, it's just simply changing its form. It's going from a solid to a liquid. That's it. So if you have a planet just filled with all this ferromagnetic material that's swirling around, why wouldn't that be the reason? But again, this is just me thinking out loud. Thought you might enjoy my thoughts for a second. But that's actually it for this lesson on the Earth's magnetic field and its magnetosphere. This is just the first part, though. It is a huge, huge lesson. There's so much to learn about the Earth. Guys, whether you realize it or not, we only know maybe, like, what? Between 1 to 5% of everything about the Earth that we could possibly know. We actually don't know that much, and we're still constantly learning all the time about the Earth. Even the oceans. But before I get lost on a scientific tangent, I gotta stop myself. Hold on. And just make sure you check back for part 2, guys. Alright? So, I hope that this refreshed your memory. I hope it was helpful. Maybe helped you even review for a test. And I'll see you guys next time. Have a great day.